Now see, we have done torque. Torque is equal to R cross F. This was actually rotational analog of force and known as moments of force or torque. Similarly, we can define angular momentum. So when the body is rotating about an axis, we also define angular momentum, and angular momentum is defined as R cross P, where r is the position vector of the particle with respect to the origin and p is the linear momentum of the particle. So, L is equal to r cross p. L is angular momentum. Direction of angular momentum, L is perpendicular to the plane of position vector and linear momentum. So, we can also write L is equal to r sin theta into p, that can be written here rp sin theta. If you are taking here again theta is equal to 0 or 180, you will be getting angular momentum L is equal to 0. But if you take theta is equal to 90, you will be getting angular momentum L is equal to R into P, that is R into mv. So, that is mvr. So, maximum angular momentum on the particle is equal to here mvr. So, now here we can go for the relation between angular momentum and torque also. We know this thing, L is equal to vector is equal to R cross P. If you differentiate it with the time, you will be getting dl upon dt is equal to R cross dp upon dt plus here dr upon dt cross p. I have applied here the product rule of differentiation. So, we can get dl upon dt is equal to r cross f. We know this thing dp upon dt, that is the rate of change of linear momentum, is equal to force plus v cross p. But v and p are in the same direction, so theta is equal to 0. So, this whole term will become 0 because vp sin theta cross product, and that will be here 0. So, you can get dl upon dt is equal to r cross f, and that is known as here dl upon dt is equal to torque. So, here that is a tau. So, the rate of change of angular momentum, that is the time rate of change of angular momentum, is equal to total external torque acting on the rotating body. It is similar to F is equal to dp upon dt, that we have done in Newton's second law of motion, that is the Newton's laws of motion. The time rate of change of linear momentum is equal to the net external force acting on the body. So, this is about the relation between angular momentum and torque. Now, see here conservation of angular momentum. We have done conservation of linear momentum in the Newton's law of motion chapter. So, here also we can do, as we know, dl upon dt is equal to external torque. If you are taking here external torque is 0, that is the symbol of tau is equal to 0. So, if there is no external torque acting on the system, then you can write dl upon dt is equal to 0, that is L is constant. It means if there is no external torque acting on the system, then the angular momentum of the system remains conserved.